Good evening. This is Math 2414. It's February the 19th. A couple of announcements to start off our lecture today. First of all, Exam 1. The testing window finished last Tuesday. I hope to have the grades posted on your D2L gradebook by Wednesday of this week. And we'll send out a remind message when the grades are posted. If you want a copy of your graded exam, send me an email, not a remind message, but send me an email if you want a copy of the graded exam. All right, no remind messages here. Make sure you do it by email. You will have some homework due on the 25th of February, this coming Sunday. I'll assign a problem today and I'll assign a problem on Wednesday for you to turn in. So I wanted to make sure we've got that done all set. Okay. Today, we are moving on with talking about integration. We've been talking about integration the last couple of days. If you remember in section 3.1, we looked at integration by parts. And so when we're talking about integration by parts, remember we have this kind of sort of like a formula, right? That if we have the integral u dv is equal to u times v minus the integral of v du. Most commonly, you see integration by parts. Not always, but most commonly, when you have some kind of a multiplication problem, parts is frequently a method to use. So I'm just going to write multiplication problems. Now remember, it doesn't have to be a multiplication problem, but that's a common situation to have when you're going to use parts, multiplication problems. And you can easily divide up the lecture into two. We were looking at trig integrals. So we were looking at integrals that involved various forms and powers of trig functions. All right, so we are, in the last section we talked about trig integrals. And so remember, trig integrals involved various forms for powers of trig functions. So, you know, we were looking at problems where you had powers of cosine x multiplied by sine x. And we looked at powers of sine x multiplied by cosine x. And so the idea there, remember in both of those forms, was to break off, if you could get a sine function or a cosine function sitting off by itself as a factor, and you could get the rest of it as powers of the other function, then you would have the power rule in both cases. Right? And so in both of these cases, we were talking about integrals that would be in the form u to the n du, right? The power rule. All right, and then, but those weren't the only forms. We also had we saw that if you could break off a secant and a tangent as a factor and write the rest of this as powers of secant x, right? That again would be a power rule problem because the derivative of secant is secant tangent. And also, if you could break off a secant squared, and you could write the rest of this, the other factor, as powers of tangent, right? You know that the derivative of tangent is secant squared. And so again, that both of those forms would be power rule problems, right? That you'd, in all of those situations, you'd have e to the u, or I'm sorry, u to the n du. And then finally, we saw kind of how to deal with even powers of sine and cosine, that if you had sine squared x dx, that you use this trig identity, that sine squared was 1 minus cosine of 2x divided by 2, and that if you had the integral of a cosine squared that you could rewrite that using a trig identity as 1 plus cosine 2x over 2. So we're looking at these various different situations where you had powers of sines and cosines and secants and tangents, and how you would evaluate, or strategies you could use to evaluate those integrals. Okay, so kind of flipping back the screen here, then we've talked about integration by parts, multiplication problems, and now we've talked about trig integrals, where you have powers of various different functions as factors, and strategies you could use to evaluate those integrals. Okay, so in section 3.3, we are going to turn our attention to still a different situation. In 3.3, the title of the section is trigonometric substitutions, or just trig substitutions. And the idea is what happens when you have an integral where you have quadratic expressions in the integral somewhere. And when I say quadratic expressions, I'm not saying that it's just a quadratic expression and that's all you have is the integral, but there's quadratic expressions inside the integrand somewhere. Okay, so in particular, we're looking at these. What we want to do is look at expressions that, or integrals rather, that involve a squared minus u squared, integrals that involve u squared minus a squared, and integrals that involve a squared plus u squared. Those three forms for quadratics. We've seen that using completing the square, that all quadratics could be written in one of those three versions right there. Now, when I'm talking about involving integrals that involve those things, I'm looking at these kinds of examples. Integrals that look like this one right here. So let's say you have dx over the square root of 1 minus 9x squared quantity cubed. Right, notice that underneath that radical you have that 1 minus 9x squared. So that's an expression that's in, that quadratic is in the expression a squared minus u squared. Or at least it's something we could write in that form, a squared minus u squared. If you had an integral in this form, dx over 1 plus 4x squared, right, that's an integral that involves the quadratic expression a squared plus u squared. You have this integral right here. So these are all just kind of examples of integrals that involve these kinds of trig expressions, where a u substitution might not be appropriate as far as evaluating the integral. So here you have the integral of x squared over 36 minus x squared. So notice this integral involves something in the form a squared minus u squared. Right, these are the kinds of problems we're talking about, and how you are going to, or how we're going to kind of evolve a strategy for dealing with these kinds of expressions. And it kind of goes like this, that if you have an expression or an integral that involves, and we'll make a little chart here, quadratic expression. So if you have an integral that involves something in the form a squared minus u squared, what we're going to do is we're going to take advantage of this trig identity to help us with that kind of expression. And the trig identity is simply a version of the Pythagorean identity for the sine and the cosine. Right? We know that 1 minus sine squared is equal to cosine squared. And so when we see a quadratic expression in the form a squared minus u squared, we're going to think of 1 minus sine squared when we try to come up with an appropriate trig substitution. And so the substitution we're going to make is that we're going to let u be equal to a sine theta. right? We're going to take advantage of the sine function here to take that quadratic expression and see if we can simplify it or rewrite it so that it's a form where we can use other things that we know about integration and actually integrate it. So let's see, the next quadratic expression, let's say we have something in the form u squared minus a squared. And u squared minus a squared is different than a squared minus u squared because it's subtraction. It matters what order you write it in. And remember, u is the variable quantity, a is the constant here when we're looking at this little chart here, right? So u is a variable quantity. Let me write that down. And when I say quantity, it means it could be more involved than just a u. And a is the constant. Okay, so u squared minus a squared, now the variable quantity comes first. And so the trig identity we might use is the fact that secant squared x minus 1 is equal to tangent squared. Let me write that over here too, up here, that 1 minus sine squared is cosine squared. And so we're going to use the secant function as our substitution here. And so the substitution will be to let u be equal to a secant theta. And then finally, the last form that we want to write out, it's going to be one of these three forms, would be a squared plus u squared. And so that quadratic expression, we will take advantage of this version of the Pythagorean identity that involves secant and tangent, that 1 plus tangent squared x is equal to secant squared x. And so our substitution here is going to be to let u be equal to a secant theta. I'm sorry, that's definitely not right. Let it be equal to a tangent theta. That's better. Like that. Okay, so now, so that kind of categorizes things a little bit, but I'm quite sure that if you are watching this, that you're going, I'm not sure how this will all play out, how this would help me in any way whatsoever. So let's just look at some algebraic expressions for a minute that follow in one of these forms here. So let's say we have the square root of 16 plus 9x squared. All right, so if we take the 16 and the 9x squared and we write those as both as perfect squares, you get 4 squared plus 3x squared. And so the forms up at the top, that a quadratic expression follows the third form, the a squared plus u squared form. Right? And so what would we do? What would our substitution be for this problem? Well, we would let, excuse me, we would let u be equal to a tangent theta. So in this case, u would be 3x, and so we'd let 3x be equal to a, which is, so a squared is 16, right? A would be equal to 4, so this would be 4 tangent theta. So 3x would be equal to 4 tangent theta. And then when we square both sides there, you get that 9x squared would be equal to 16 tangent squared theta. Right, when we make that substitution. So now look what happens when we make the substitution into this algebraic expression right here. Right, I'm going to go ahead and put this in a different color here. So this would be the square root of 16 plus, but using this substitution, 9x squared has the value 16 tangent squared theta. So the new trig expression using that substitution would be the square root of 16 plus 16 tangent squared theta. Now watch what happens. You factor out the 16, and you have 1 plus tangent squared left right there. And then what's 1 plus tangent squared equal to? 1 plus tangent squared is equal to secant squared. And so this would be the square root of 16 secant squared theta. And as long as we make the assumptions about secant theta here, that secant theta is positive, right? So that would mean secant theta is positive when you have a quadrant 1 or 4 angle, right? In other words, theta is between 0 and pi over 2, or between 3 pi over 2 and 2 pi, for example, then we could write that this is 4 secant theta right here, right? Using that, making sure we keep in mind that assumption that we're making about the secant function. And so what have we got? We've got this, if you look at it, we've got this sort of complicated algebraic expression, and then using this trig substitution right here, that 3x is equal to 4 tangent theta, we were able to take that somewhat complicated radical that has a quadratic under it and rewrite it simply as 4 secant theta. And that could be a big help when you're trying to evaluate an integral. Notice you always have to kind of hedge your bets here. It doesn't mean necessarily that it is going to help you, but we are saying that it could help you. Okay? All right, so that's one example there where the algebra, there's no integral here at all. We're not doing any integration. All we're doing is looking at the trig and the algebra and how we could manipulate these expressions and maybe change the way they look a little bit. All right, so let's look at another expression. So let's say, oh, and by the way, let me go back to the previous page here really quickly. And let me copy down one more time this little chart we have here. So we have this on the next page also, so we can look at it. So I'm going to copy that and then bring it over to the next page here, paste it in. And I think I might want to have this on each page right now for a little while we're working through these. All right, so the next example, just again, an algebraic expression, would be the square root of 36 minus x squared. Square root of 36 minus x squared. Okay, so we go up to the top and we look at what quadratic expression that matches up with, and that matches up with a squared minus u squared. The 36 minus x squared it does. And so our substitution here would be to let u be equal to a sine theta in this form. Right, so in our problem, what would we have here? We would have that a is equal to 6, and u would be equal to x. And so what would our substitution be? It would be that x is equal to 6 sine theta. And so then squaring both sides, you'd have x squared is 36 sine squared theta. Okay, so now we substitute. Go ahead and do this in a different color here. So now substitute into the algebraic expression. So you have the square root of 36 minus x squared. But this would be the square root of 36 minus, and x squared would be 36 sine squared. Like that, right? Just making the substitution there. And then watch what happens. The radical is going to drop out again, isn't it? Because you factor out a 36 and you have 1 minus sine squared theta. And then 1 minus sine squared theta is cosine squared theta, using the Pythagorean identity. And then again, making the assumption that the cosine of theta is positive here, which generally that's not going to cause us too much issue, then this is going to be 6 cosine theta. So in this problem, what happened? We started with that algebraic expression. We made this trig substitution right here. We let x be 6 sine theta. And when we make the substitution, this algebraic expression simplifies simply as 6 cosine theta. And 6 cosine theta could be considerably simpler as far as trying to write out our substitution here and everything. So, or trying to evaluate an integral, I should say. Okay, so let's look at one more problem. Let's say we have the square root. And let's do something maybe sort of sort of complicated here. Let's say we have 25 times x plus 3 quantity squared minus 81. Kind of a yucky expression right there. And And so if you're looking at the quadratic expressions that this would match up with, you have a variable squared minus a constant squared. If you could write this quantity as 5 times x plus 3, like so, quantity squared minus 9 squared, like that. Right, so this matches up with the form u squared minus a squared, right, where u is equal to 5 times x plus 3, and a would be equal to 9. And so our substitution in this problem, go up to the chart at the top. The substitution here would be to let u, which is 5 times x plus 3, be equal to, and let's actually write that out. That we have u is going to be equal to a secant theta. That's going to be our substitution. So we'd have 5 times x plus 3 is going to be equal to 9 secant theta. And then when you square that expression, you'd have 25 times x plus 3 squared is equal to 81 secant squared theta. And so now we substitute. And so we take our algebraic expression, and in place of that 25 times x plus 3 squared, we would write 81 secant squared, and that would be minus 81. And notice this we've written all these so that the Pythagorean identities will help us. So notice when you factor out an 81 here, you're left with secant squared theta minus 1. And secant squared theta minus 1 is tangent squared. So you have the square root of 81 tangent squared x. And then that, as long as the tangent is positive, we would have that that's 9 tangent x. And so once again, what have we done? We've taken something that's an algebraic expression that looks pretty messy and may cause us a lot of difficulty when we're trying to integrate. We make a trig substitution. In this case, 5 times x plus 3 is equal to 9 secant theta. And when we make that substitution, that algebraic expression simplifies simply as 9 tangent x. All right, so that's the strategy we're going to use. And so we're going to see how this works out with actual problems now. And that's what we're going to do the rest of class today, is work some problems, see how these work out, maybe look at an application that ends up involving a trig substitution at the very end of class today. And, the more of these examples probably that you see in the different situations that come up, probably the better. So here's our integral. We have 9x cubed divided by the square root of 1 plus x squared. And let me move this down here. We want to go ahead and paste in our little chart here again, which I meant to do. So there's our chart. Okay, so you identified the algebraic expression, or the quadratic expression that's in your integral. This should be a dx here. And so you've got that 1 plus x squared in there, right? That 1 plus x squared matches up with a squared plus u squared, right? Where a would be equal to 1 and u would be equal to x. And so what we're going to do here is we're going to make this trig substitution. We're going to let, according to the chart up at the top, what would we be doing? We want to take advantage of the trig identity 1 plus tangent squared equals secant squared. And so we're going to use the tangent function for our substitution. We're going to let u be equal to a tangent theta. So in this case, this goes pretty easy. You just get that u is going to be equal to tangent theta, 1 times tangent theta. All right, and so if I'm sorry, and I said u equals tangent theta. I knew I was writing something down that wasn't quite right. That's going to be x equals tangent theta, because u is equal to x. So you have x equals tangent theta. And so now the idea, just like any substitution with an integral, is you've got to try to deal with all of the different expressions in there. And so, you want them all in terms of theta. So this 1 plus x squared, we're going to be able to deal with that here with the x equals tangent theta. And then you've got x cubed. Well, I've got x right there as tangent theta again, so I can substitute there. Dx is something I don't have yet. And so I would need to write dx down also. So if x is tangent theta, then dx would be secant squared theta d theta. And so now I have all the pieces to this integral, and now I can substitute. So now substitute. And what we're doing, like any substitution, we're trying to take the integral and change it from x's over to thetas in this case. So 9x cubed would become 9 tangent cubed theta, right? Because x is tangent theta. And then in the denominator, we have that radical. The square root of 1 plus x squared would become the square root of 1 plus tangent squared. And then dx would be secant squared theta d theta. Now don't panic here. Please don't panic. What's going to always happen is that the integral is going to first briefly look a lot worse than it started out when you shift over to these trig functions. But then if you can simplify it, you'll find that it will typically end up being in a form where you can use things that you know about the trig functions as far as evaluating the integral. All right, so let's see how this would work out. So in our denominator, let's see, we have, well, first of all, in the numerator, we have 9 tangent cubed theta, and then we have secant squared theta d theta. And let me go ahead and write the d theta just adjacent to the fraction here. That would probably be typically how it's written. And then the denominator, I have the square root of, and 1 plus tangent squared is equal to secant squared. That is why we made this substitution, this crazy substitution. Because now what's going to happen here, you have 9 tangent cubed theta, secant squared theta in the numerator. In the denominator, as long as secant is positive, this would just be secant x. And then you have dx there. I'm sorry, secant, I apologize, it would be secant theta and d theta. That's better. All right, and so then what happens there? The secants divide out, right? And so you're left with a trig integral that's very much like the problems we saw in the last section. By the way, if you have not gone through that last section, you're going to need to, because those kinds of integrals are going to come up after you deal with trig substitution. So this is powers of secant and tangent. And so remember, the idea here is, like we talked about earlier in the lecture today and last time, is with secants and tangents, what you'd either like to break off is a secant and a tangent or a secant squared. Now, I don't have a secant squared here at all to break off, but I do have a secant and a tangent. So I'll take the 9 outside the integral. I'll take the tangent, and I'll break it up. I'll write it as a tangent squared, and then I have another tangent here. And remember, the key here is that I've got this secant tangent right here. Right? And so when I have that secant tangent broken off, then the rest of the integral, the other factor, has to be a power of secant. And so what we do is we rewrite tangent squared as secant squared x, secant squared theta minus 1. And then that would be times secant theta tangent theta d theta. And so notice then this is going to end up being the power rule, right? So you're going to have a secant squared times secant tangent, that's u squared du. And so this would be 9 times 1/3 secant cubed theta. You remember you're using the distributive property here, so that secant tangent gets multiplied by both of those terms. So you have a secant squared times secant tangent. That's u squared du. So that's where I get the 1/3 secant cubed from. And then you have secant theta tangent theta times 1. And so the antiderivative for that term is simply secant theta. And then plus c, like that. Now, this is, so we've evaluated the integral, we've written down an antiderivative. The problem is this antiderivative is with respect to theta, and we need the antiderivative to be with respect to x, right? So the antiderivative must be with respect to x, because that was the original variable. And so what we're going to do here is we're going to write down some of the pertinent information in this problem on the next screen and kind of see how this is going to turn out, how we're going to go to x's here. All right, so now remember the original problem was this integral, 9x cubed over the square root of 1 plus x squared dx. And then we made this substitution that x was equal to tangent theta and that dx was equal to secant squared theta d theta, right? We made that substitution. After we made that substitution and found the antiderivative of that trig expression, we ended up with this form, 9 times 1/3 secant cubed theta minus secant theta, and then plus c. All right, so now what we need to do is now go back to x's. Now go back to x's, but the question is, but how? Right? How do you do that? And this is where our substitution comes into play. So let me show you a little geometry trick we can use to actually go back to x's here. We take our substitution x equals tangent theta, and we actually label a right triangle and use right triangle trigonometry to help us through this going back to x right here. And what we'll do is we'll label one angle in the triangle theta. So when we do that, right, what do we have here? We have the tangent theta, because of our substitution, is equal to x over 1. And remember that the tangent function is defined to be the opposite side over the adjacent side. So in our picture right here, what that would mean is that the opposite side from theta would have to be x, and the adjacent side would have to be 1. And then using the Pythagorean theorem, the hypotenuse for this right triangle would be the square root of x squared plus 1. So this triangle is going to allow us to take our integral and shift back to x's. See, because look, what are we going to do here? We have secants in our expression here, right? And so from this picture, what can we see? That secant theta, now remember, secant theta is the reciprocal of the cosine, and the cosine is adjacent over hypotenuse. So secant would be hypotenuse over adjacent. And so the secant of theta would be the square root of x squared plus 1 from our triangle divided by 1, or just the square root of x squared plus 1. So what that implies, or what that tells us, is we can go back to the trig expression we have at the top. If we want to shift it back to x's, we can do that by every place we see a secant, replace it with the square root of x squared plus 1. And so our integral becomes 9 times 1/3, or I shouldn't say our integral, but our antiderivative becomes 1/3 times secant cubed, but secant is the square root of x squared plus 1, so this would be the square root of x squared plus 1 cubed, minus, and then secant theta, which would just be the square root of x squared plus 1, and then plus a constant. If you wanted to, you could rewrite everything in terms of fractional exponents. I could also multiply through by 9, and I would get 3 times x squared plus 1 to the 3 halves minus 9 times x squared plus 1 to the 1 half plus c. And we have the antiderivative for our function. Right? That's the whole goal here. All right, so the idea then is to identify the form of the quadratic expression you have. So in this case, we looked at that 1 plus x squared, and that told us what trig substitution to use using that little table I have at the top. And then, just like any substitution, you need to calculate all the different pieces of the integral and rewrite them all in terms of theta. Then once you've got the integral with respect to theta only, then you go through and see if you can evaluate that new integral. And then you just have to remember to go back to x at the end. Right? That's a key. And that's a common mistake because students forget to do that. All right, so let's look at another example for this. Let's say we have x squared over the square root of 36 minus x squared dx. And once again, I want to move this integral down here. And let's go ahead and paste in our chart. So we have that sitting here on the top of the page. So in this case, the square root of 36 minus x squared, right, that matches up here with the a squared minus u squared. And so our substitution here is going to be that form, where 36 minus x squared matches up with a squared minus u squared, where a would be 6, u would be x. All right, so the substitution here then would be to let u, so in this case this is x, is going to be equal to a sine theta. So this would be 6 sine theta. That's what x is going to be. And then if x is 6 sine theta, then x squared would be 36 sine squared theta. And then dx would be equal to 6 cosine theta d theta. Right, so you want to match up the quadratic expression with the proper form up at the top of the screen there. Then figure out what a and u are from there, and then that will allow you to calculate the substitution you need to make. So we're going to let x squared be equal to 36 sine squared theta. So we go now to our integral, and so I'll go ahead and make my substitution. So in place of x squared in the numerator, we have 36 sine squared theta. In the denominator, you have 36 minus x squared, so that would be 36 minus x squared would be 36 sine squared theta. And then dx, please don't forget the dx, would be 6 cosine theta d theta. All right, so once we've made the substitution and written everything in terms of theta, there's our new integral right there. All right, so now the idea is to try to simplify this as best we can and see what happens. Now, the 6 and the 36, I can multiply those, and so that's 216 that I'll bring outside. Right, 6 times 30 is 180. 6 times 6 is 36. So you get 216. And then in the numerator, I have sine squared theta, cosine theta. Right, d theta alongside the integral, and then under the radical, we'd have 36 times 1 minus sine squared theta. All right, so take your time as you go through this. In the denominator, the square root of 36 times 1 minus sine squared would become the square root of 36 cosine squared theta. And as long as cosine is positive, we can rewrite this. Let's see, we'll have sine squared theta, cosine theta in the numerator. In the denominator, this would be 6 cosine theta, and then d theta, like that. Now the 6 will come out and divide into the 216 36 times. So you have 36 times, and then one of the cosines divides out, or the cosine divides out, and so we are just left with sine squared theta d theta. That is an integral that we can definitely work with, right? We know how to deal with that kind of an integral. So what's going to happen there? We remember how you deal with the even power of the sine or the cosine. We talked about that again earlier in the lecture today. We use this identity, that sine squared theta is the same as 1 minus cosine of 2 theta divided by 2. Right, that's a trig identity, remember. And so that 1/2 comes out and divides with the 36 and leaves us with 18. And then we're just down to this integral, 1 minus cosine of 2 theta d theta. So that's not too bad. We have 18 times the antiderivative for 1 d theta. Be careful, that's just theta. And then for cosine of 2 theta, you'll end up with a 1/2 as a factor, and then this will be sine of 2 theta. And then plus a constant. Now we're going to use our right triangle trick here on this problem. Let me give myself a little bit more room here. But I've got a 2 theta in there, and so it would be nice to deal with that 2 theta and get rid of that using the double angle for the sine. So this would be 1/2 times 2 sine theta cosine theta, like that, plus c. That could come up, and so you need to be careful with that. And then it works out nice because the 2's divide out, so you have 18 times theta minus sine theta cosine theta. Cosine theta, and then plus c. And so now I'm going to use my right triangle trick here to see if I could come up with expressions for theta, for sine theta, and for cosine theta. Okay, so let's see. Let's go see the next screen here. So in my problem, remember the original problem, let's write that down again, is x squared divided by the square root of 36 minus x squared dx. I made the substitution that x was equal to 6 sine theta, and the dx was equal to then to 6 cosine theta, 6 cosine theta d theta. All right, and then we got, dot, dot, dot here. We went through the substitution, and going back, we've got that this is 18 times theta minus sine theta cosine theta plus c. That was our antiderivative. All right, so now we're going to use x equals sine theta to label a right triangle. And that right triangle will allow us to write out this expression in terms of x. So I'm going to say use the triangle to go back to x. So in the triangle, to label it correctly, so we have theta right here, and you've got that x over 6 is equal to sine theta, or just divide both sides by 6 there. Sine, remember, is equal to opposite over hypotenuse. So labeling the triangle, then the opposite side from theta would be x, and the hypotenuse would be 6. And so then using the Pythagorean theorem, the third side would be the square root of 36 minus x squared. And so from that triangle, what can we say here? That we can tell that sine of theta is equal to, we've already seen that, sine of theta is equal to x over 6. But cosine of theta, which would be adjacent over hypotenuse, would be the square root of 36 minus x squared over 6. And then what about theta? Well, we've got, so there's still a little bit more to do here. You've got that sine of theta is equal to x over 6. So that means that theta is arc sine or inverse sine of x over 6. So those are the pieces we need. I'm going to put a box around all three of those. Those are the three pieces we need to take our integral, or our antiderivative, and write it in terms of x only. So you have 18 times theta, which would be arc sine of x over 6, minus sine theta times cosine theta, so that'd be x over 6 times the square root of 36 minus x squared over 6, and then plus c. And so finally, this would give me, there's a lot of ways you could write this at the end. Definitely would not make a big deal about how you wrote this at the end at all. So do not get hung up on that at all here. So I'll just write this as 1 over 36 times x times the square root of 36 minus x squared, this second term there, and then plus c. Okay, so it's it's definitely not a straightforward process at all when you're evaluating these integrals. There's definitely a lot going on. And so we definitely want to look at another example here and see how this works out. All right, so let me make sure to remember to paste our little table at the top here. So there's our little table. And so our problem that we're going to look at in this page is the integral of the square root of 9 plus 16x squared dx. All right, so first of all, this integral would become the square root of 3 squared plus 4x squared dx. And if you look at the top, the format we're using is we're certainly looking at a squared plus u squared as the quadratic expression we're trying to deal with, where a would be equal to 3 and u would be equal to 4x. And so our substitution that we're going to use is u equals a tan theta. So in this case, 4x would be equal to 3 tangent theta. So 4x is equal to 3 tangent theta, then 16x squared would be equal to 9 tangent squared theta. And also, if 4x is equal to 3 tangent theta, then x is 3/4 tangent theta. And remember, you're going to always end up having to find dx as part of the substitution. So dx would be 3/4 times secant squared theta d theta. All right, so lots to substitute here. So let's see how this works out. So when we go to our new integral, the integral with respect to theta, we have the square root of 9 plus 9 tangent squared theta. And then that would be dx, and dx would be equal to 3/4 secant squared theta d theta. All right, and so then you got to simplify this. So this radical, factor out a 9, and you get 1 plus tangent squared theta. The 3/4 I could take outside the integral, and then you have secant squared theta d theta here. So that would give you the square root of 9 secant squared theta, and then this would be times secant squared theta. Square root of 9 is 3, and then you can take that 3 outside the integral, and so that would be 9/4, and then the square root of secant squared would simply be secant theta times secant squared theta d theta. All right, and so that integral, this is interesting, is 9/4 times, and then this would be the integral of secant cubed theta d theta. Now, secant cubed theta d theta, that ends up being a problem we did in class in the last lecture. But secant cubed d theta is an integration by parts problem. We did that in class last time. So I would say see the notes from 2/14/18, February the 14th, Valentine's Day. We actually did secant cubed theta. And so you end up with 9/4 times the antiderivative for secant cubed. And I'm just going to take that answer from that lecture, which is secant theta tangent theta plus natural log of secant theta plus tangent theta, and then plus c, like that. So it's kind of a messy expression. And by the way, you know, like I said, that was from the lecture last time. It was towards the end of class. And there's also a 1/2 as part of that integral. So there's a 1/2 sitting there in front. And so now what you need to do is you need to get a right triangle and label it and see how we can rewrite this integral. And, you know, maybe have some semblance of being able to squeeze this into this page. So there's our right triangle. There's the angle theta. And we know from our substitution that the tangent theta is equal to 4x over 3. Right? Tangent theta is equal to 4x over 3. And so we labeled our right triangle. Remember, the tangent is opposite over adjacent, so this would be 4x and 3 in our right triangle. And so that gives us that the third side would be the square root of 9 plus 16x squared. Like that. And so what else do we need for our substitution? Well, we need secant theta. And so secant theta would be the square root of 9 plus 16x squared divided by 3. Right? A hypotenuse over adjacent. And so the integral becomes kind of messy, becomes 9/8 times secant theta times tangent theta. And so that would be 4x times the square root of 9 plus 16x squared over 9, right? Because it's 3 times 3, plus the natural log of absolute value of the secant of theta, which is that radical, 9 plus 16x squared over 3, plus 4x over 3. Close off the absolute values there. Close off the brackets, and we put plus c. All right, now, and that's the antiderivative. It's really pretty messy. Now, that natural log is the last step. Well, I want to show you something that if you're going to check your answer, like some of you want to check your answers all the time in Wolfram Alpha or something like that, or you're going to use some other technology to try to look up your answer, you may not see that natural log exactly look like I have it written right there. You may see the problem like this if you check your answer in the back of the book. You may see this answer instead. All right, now let me show you what's going on here. So now this is our answer from the last page. It was 9/8 times 4x times the square root of 9 plus 16x squared, all divided by 9, and then plus the natural log of the absolute value of the square root of 9 plus 16x squared over 3 plus 4x over 3, and then plus c. But like I said, you may see another answer. And this might be what you see. You might see 9/8 times 4x times the square root of 9 plus 16x squared over 9 plus, but this logarithm, you might see it written completely differently. Well, not completely differently, but definitely different. Where that 3 in the denominator is not even present there anymore, and you just have just the natural log of the sum of the numerators there. So what the heck is going on in that form right there? And the deal is this, is that if you look at the natural log of the absolute value of the square root of 9 plus 16x squared over 3 plus 4x over 3, that first of all, you could combine those fractions as one fraction, all over 3. See, and that's a logarithm of a fraction right there. And you have the quotient rule for logarithms that says that that's the natural log of the numerator. So that'd be the natural log of the absolute value of 9 plus 16x squared plus 4x, and then minus the natural log of the denominator, just the natural log of 3. Technically the absolute value of 3, but 3 is positive, and then plus c. See, that's the deal, is natural log of 3 is a constant. And c is a constant, so what you're doing is you're just combining c minus the natural log of 3, and you're saying that if c is an arbitrary constant, then c minus the natural log of 3 is still an arbitrary constant. And so what they do is they just combine them to write it in a somewhat simpler form, right? And so it's equivalent to say that it's just the natural log of the square root of 9 plus 16x squared plus 4x inside the absolute value, and then plus a constant, right? And so that's common to see that, and so I wanted to point that out in case you were confronted with that and you weren't sure what to do, right? Okay, so let's finish the day maybe by looking at one last problem, and then that will finish up what we're going to do. And I tell you what, let's do a definite integral to finish the day with. And I still want to put in our little chart here at the beginning, even though it takes up some space. I think it's worthwhile to have that written there. Okay, so this will be our last problem of the day. And that'll give us a good set of examples to work through on trig substitution. So this is the integral from 4 to 8 of the square root of x squared minus 16 over x squared dx. Okay, so that x squared minus 16 is going to be u squared minus a squared. That's the form we're taking. And so the substitution we're going to use the trig identity secant squared minus 1. And so our substitutions to let u equal a secant theta. Right, where in this problem, u would be equal to x, and then a would be equal to 4. Right, so you have x is equal to 4 secant theta. So if x is 4 secant theta, then dx would be equal to 4 secant theta tangent theta. And we're ready to do the substitution. Okay, so let's make the substitution here. Now notice I'm not writing the limits of integration because I'm about to change those limits of integration. In fact, I could go ahead and do that right now. You know that x is 4 secant theta. So when x is 4, right, that's the lower limit, you get 4 equals 4 secant theta. So you have 1 is equal to secant theta. And so secant of theta is equal to 1. Good news there is that theta has got to be equal to 0. Secant of 0 is equal to 1. And then when x is equal to 8, right, you have 8 equals 4 secant theta. So you have 2 is equal to secant theta. So secant theta is equal to 2 when cosine theta is equal to 1/2. And in quadrant 1, the cosine of theta would be equal to 1/2 when theta is equal to pi over 3. So our new limits of integration are going to go from 0 to pi over 3. And that means I don't have to go back to x's at the end of my problem. All right, so I make my substitution. So this would be the square root of x squared minus 16. So that would be 16 secant squared theta minus 16. In the denominator, you have x squared, which would be another 16 secant squared theta. And then dx would be 4 secant theta tangent theta d theta. Okay, so you got a lot going on here, but no different than any of the other problems we've done so far. So in the denominator, let's see, I took the 4 and the 16 out. The 4's in the numerator, the 16's in the denominator, so that's a 1/4 out front of the integral. And then you have the square root of 16 times secant squared theta minus 1. And then that would be times secant theta tangent theta d theta. So secant squared theta minus 1 is going to be equal to tangent squared theta. So you have the square root of 16 tangent squared theta times secant theta tangent theta d theta. Square root of 16 is 4, and so notice that's going to divide out with the 4 that's outside the integral, so that's good. And then you have the square root of tangent squared, which is tangent, and so you'll have secant times tangent squared. And I think there's, oh yeah, I knew there was something I forgot. There's a, in this form right here, there should be a secant squared in the denominator here. That's better. Okay. So I'm sorry I forgot that. So there's that secant squared theta right there. So the 4's divide out, like I said, and then the square root of tangent squared is tangent. So let me take another step here, since I kind of messed that up slightly. So you have tangent theta over secant squared theta, and then you have times secant theta tangent theta d theta. So we're getting close. So this would be the integral from 0 to pi over 3, and you're going to have a tangent squared in the numerator and a secant in the denominator d theta. And you can get hung up on all sorts of crazy ways to try to deal with that integral, but you know, there's a very basic way to look at that one. And that's simply to write tangent squared as secant squared theta minus 1. See, now you can divide it out term by term. And you get the integral from 0 to pi over 3 of secant theta minus, and then 1 over secant theta is simply cosine theta. So it turns out really nice there at the end. So the antiderivative for the secant is natural log of the absolute value of secant theta plus tangent theta. And then the antiderivative for cosine is sine. And then that goes from 0 to pi over 3. So putting pi over 3 in place of theta in there, you get the natural log. The secant of pi over 3 is 2. The tangent of pi over 3 is the square root of 3. And then minus the sine of pi over 3, and the sine of pi over 3 is the square root of 3 over 2. So at the upper limit, you get that expression. The lower limit, you end up with the natural log, so this is minus the natural log of secant of 0, but secant of 0 is 1. And then sine of 0 is 0. And tangent of 0 is 0. So all that just goes away because the natural log of 1 is 0. So I'm just going to go ahead and erase that, right? Because that's the lower limit's all 0. And so you're left with this answer right here. That's our exact value for the value of the indefinite integral. Okay, so that's another good problem to look at. So we've seen several good examples here for trig substitutions and different things that come into play with trig substitutions. So I would recommend having this little chart that I've been putting at the top of each page, above each problem, writing that down, trying to work your way through the substitution that you've got to make. That's the critical thing, is to decide which substitution you're going to make. And so you have to look at what kind of quadratic expression you've got, which of those forms you have, and then think about the trig identity that goes with that particular quadratic expression, and then that will allow you to figure out the substitution. All right, so I think that's where we're going to shut it down for the day. I do want to point out, let's see, so homework on the next page, in case you're looking for it. So your first homework problem to turn in on the 25th. So due February 25th. This is section 3.3, problem number 138. So I give you one problem today and either one or two problems on Wednesday to get turned into me on Wednesday of this, or on Sunday of this week. Okay. So with that in mind, then